Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. It took tens of thousands of years for mankind to understand the nature of the solar system, with a star and bodies orbiting around it. Then it took centuries to detect and name all the main planets in the solar system, and understand that the stars in the sky were countless other suns, parts of a galaxy. But it took only years to detect and name thousands of planets that do not belong to our system. Exoplanets. We're going to space again tonight for another cruise among the stars. And this time, I'm taking you to exoplanets, the billions and billions of planets that exist in our galaxy alone, which astronomers have started to discover rather recently. The identification of exoplanets is still a young discipline, so we're going to dream about those faraway worlds. We will spend our cruise traveling to some of them, like Proxima Centauri B, OTS 44, and Kepler 438b. And to entertain you along the way, I will tell you about the different types of planets and how we think they form, as well as the different types of stars, because not all stars are like the sun. We'll explore how planets that are so far away can be discovered. Another big question raised by the evidence that so many planets exist in the universe is, could there be life on them? And what kind of life? This field of investigation, which studies the possibility of extraterrestrial life, is called astrobiology. And we'll talk about it too. So that gives us a lot to discover tonight. But don't worry about the apparent complexity of all this. Even if you have no knowledge of physics and astronomy, it's all going to be easy to understand with examples taken from daily life that will make these concepts sound familiar to you. If you like this type of exploration journey in space, there are various others available on my channel, like those in the solar system. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3 per month, but it doesn't mean you will get less. We let people contribute what they wish to or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. You will gain access to several exclusive episodes, and also to all our episodes with and without background sounds. We also offer advance releases to our patrons. We have added links to Patreon, as well as links to different streaming options, which may be better suited for you. You will find these links in the description of the episode, along with timestamps to allow you to resume the episode wherever you left off, in case you do fall asleep. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now assume a comfortable position. Maybe move a little bit to settle. Take a long, deep, relaxing breath, and when you slowly exhale, Feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, let's begin our journey among the stars. It took only a few years since the 1990s to discover and name hundreds of exoplanets, planets that do not belong to our solar system. Knowledge in astronomy has advanced much faster than our ability to travel in space. And these new planets are so far away from us that the hope of seeing human beings reach them one day is tenuous. But tonight, by the power of imagination, we are going to travel much faster than light and cross light years and seconds to reach our destination. Of course, everything we will visualize tonight is hypothetical. It is based on observation, deduction, and the state of our scientific knowledge. It is likely that the way we understand other systems and exoplanets will keep evolving. But still, there have been so many discoveries and so much progress in this field in the past 30 years that it has become a major aspect of modern astronomy. Our first stop on this journey will be at the nearest exoplanet that we know of, Proxima Centauri B, 4.2 light-years away from Earth. But how is it possible to detect planets that are so far away? The last big planet in the solar system, Neptune, was discovered in the 19th century. Then there was Pluto in 1930, which has been reclassified as a dwarf planet. But these are only a few hours' light away from us. Proxima Centauri B is hundreds of times farther, and no conventional telescope can actually take a picture of it. So, as we begin to accelerate, we are already leaving the solar system, and we will arrive at Proxima Centauri in a few minutes. Let's take a look at how exoplanets can be discovered. Any planet orbiting around a star is a very faint light source compared to its parent star. For example, in the solar system, the sun is 1 billion times as bright as any of the planets that orbit around it. When you watch from several light years away, the light from planets is barely existent and gets completely washed out by the star they're attached to. So very few exoplanets have actually been observed directly, and astronomers resort to indirect methods to discover them. The first method is called Transit Photometry. What does it mean? Seen from Earth, other stars in our segment of the galaxy have a relatively stable brightness. It can increase or decrease with their distance to us because of all the planetary systems moving, orbiting the center of the galaxy at different speeds. But this is predictable. However, if there are planets orbiting these stars, these planets may regularly cross between the star and us. And this transit will hide a little bit of the star's light, not much of it, and it depends on the size of the planet and its distance to the star. But with instruments that are precise enough that a little variation in brightness can be detected during the planet's transit in front of its star. Sometimes the star dims significantly. There are examples with big exoplanets that make the visual brightness drop almost 2%. Most of the time, it is much less than that. For example, a planet the size of Earth transiting in front of a star the size of the Sun produces a dimming of only 0.01%. This is tiny, but still predictable with the right instruments. This method is complicated because there are many variables. The star may have several planets. It requires making assumptions about the characteristics of the planet's orbit. The dimming of light during transit is so small that errors, false positives, or transits that are not observed are probably frequent. It also requires the planet's orbit to be aligned in the right plane from the astronomer's vantage point. From where we are, there are planets that will never transit just in the right line of sight of their star. So it works, but only a minority of planets can be detected this way, and the larger their orbit, the less likely they are to be found. A second method that sounds very complicated, but the concept is not, is the use of radial velocity and Doppler spectroscopy. So what is this about? You know that planets are attached to a star by gravitation. This force keeps them in orbit around the star because the star is way more massive than them. But gravitation works both ways. The star has a major influence on the planet's orbits. And given that the planets are also massive objects, they have an influence, much smaller, on the star too. The bigger the planet and the closer it is, the more influence it has on its star. This means that the center of mass in a star system is not the exact center of the star. This center of mass is generally inside the star, but it's not the exact center of it because of the influence of planets. We generally say that planets orbit around the star, and this makes sense because the star in a system represents the bulk of matter, typically around 99% of it. Technically, planets and the star itself orbit around the center of mass, which happens to be inside the star if it's big enough. But a little bit uncentered. This means that the star also has a little orbit. It moves around a gravitational center. For example, in the solar system, Jupiter makes the Sun move by 13 meters per second. Earth also has a little influence on the Sun. It is much smaller than Jupiter due to Earth's smaller mass, but it influences the Sun by about 9 centimeters, a bit more than 3 inches per second. This is the concept of radial velocity, and these little interferences of the planets on their star can be detected. How? Thanks to a phenomenon called the Doppler effect. Light has the properties of a wave, and when you receive a wave emitted by a moving object, waves arrived a little bit distorted. Let's take the example of the Doppler effect with sound waves that we experience every day. You may have noticed that when an ambulance with a siren passes near you in the street, the sound of the siren changes quite a lot. When the ambulance is advancing towards you, the sound is higher pitched. Then it passes just near you, and the sound becomes lower pitched as it moves away. The same happens when you are near a railroad. The sound of the train changes a lot depending on whether the train comes towards you or moves away. This is not due to a variation in the sound from the siren or the train, and someone on board the ambulance would not perceive a different kind of sound. This is because sound waves are emitted by an object that is in motion relative to you. Try to imagine the waves as an undulating line. The waves from the siren are coming toward you, but so is the vehicle, and this tends to compress the line. It fluctuates faster. In other words, the frequency increases, and this makes the sound seem higher pitched. Now, when the vehicle moves away, the waves are more distant. The frequency decreases, and they sound deeper. This modulation of waves due to motion is the Doppler effect. Sound waves are useless in space because sound propagates through matter, through air in this example. But in the void of space, sound waves couldn't travel. But we have light instead. That's the basis of the Doppler Spectroscopy, detecting and measuring how the motion of a star is affected by the planets, thanks to the variation in light waves. In practice, this is very complex. It requires extremely precise instruments and calculations, and velocity variations down to 3 meters per second from stars that are several light years away, or even thousands or hundreds of light years away, can be detected with modern spectrometers. A spectrometer is an instrument that measures and separates the spectrum of light. And in astronomy, spectrometers can even analyze the chemical composition of faraway stars and planets, thanks to the signature of the elements they are made of. We'll come back to that later. There are such high-precision systems searching for exoplanets thanks to Doppler spectroscopy in Hawaii and in Chile. They are responsible for the discovery of thousands of planets. Apart from the two methods we have discussed, Transit Photometry and Doppler spectroscopy, there are more methods to discover exoplanets. A visual method, which currently works only for very large planets like those the size of Jupiter with short orbits. It involves detecting how the light reflected by a planet varies. Planets go through phases like the Moon, reflecting more or less light through a cycle, depending on their orbit and how they are positioned. Telescopes cannot distinguish them from their stars, but they can measure how the same cycle of variations in brightness repeats itself and deduce the existence of planets this way. Another method is called pulsar timing. It is limited to planets that orbit pulsars, a type of dead star. We'll talk about the types of stars a little later during our cruise. Pulsars are very dense bodies that rotate and emit radio waves with extreme regularity, making it possible to track the motion, possibly of planets, with extreme precision. Pulsar timing can reveal planets with less than 1/10 the mass of Earth, and can even detect mutual gravitational perturbations between various members of a planetary system, revealing several planets and how they interact at the same time. There are not many planetary systems with a pulsar at their center. They have to be very old systems with an exhausted star that has already collapsed on itself. As you see, these indirect methods are a bit complicated and have a margin of error. But they work and have allowed the discovery of thousands of planets. As of January 2025, there are 5,830 exoplanets that have been confirmed in 4,354 different systems. We are now approaching our first stop, Proxima Centauri B. We are now 4.2 light-years away from Earth, approximately 25 billion miles away. Alpha Centauri is a star system, like the solar system, and the closest to us in the galaxy, but it looks quite different. There is not a single star, but 3 stars. 2 larger and look like smaller versions of the Sun. And one is a smaller star called a red dwarf. In 2016, the discovery of Proxima Centauri B, a rocky planet orbiting the red dwarf star, was unveiled. Interestingly, this planet is in the so-called habitable zone of the star, not too close, not too far, similar to Earth's position in the solar system. Another thing in common between this exoplanet and Earth is the size. Proxima Centauri B may be a bit bigger, at 1.3 times Earth's mass, but the kind of gravity at its surface is probably acceptable for most terrestrial life forms, including humans. But this doesn't mean the planet is another Earth, but it's likely to be habitable. We don't know exactly what it's made of. It could be rocky like Earth, or it could have an icy composition like Neptune, with a thick layer of hydrogen on its surface. The star, Proxima Centauri, is the closest to the Sun, but it is not visible to the naked eye from Earth. Unlike stars that are farther away, because red dwarfs do not emit as much light as Sun-like stars. One challenge for the possibility of life as we know it on Proxima Centauri B is that the star is a flare star. Occasionally, it undergoes dramatic increases in brightness and emissions of all sorts. When these stellar storms happen, it is estimated that the surface of the planet is intensely irradiated to levels of UV rays that would easily kill the most resistant microorganisms on Earth. Proxima Centauri B is hit by intense stellar wind too, which would probably carry away any atmosphere, unless the planet has a powerful magnetic field like Earth that would shield it from stellar wind. What is stellar wind? You know that stars emit light and heat and other radiation, but they also release matter, such as gases or particles, including free electrons and atomic nuclei. The Sun does it too, but on Earth, we are protected from this stream of particles by the Earth's magnetic field, which deviates solar wind. In case of Proxima Centauri B, it is uncertain whether there is a magnetic field, and the stellar wind is up to 2,000 times more powerful than on Earth, making an atmosphere made of gas unlikely. In this case, life forms would have to exist underground, or they would have to be life forms we have a hard time imagining. Yet it is not completely impossible, because the planet is in the habitable zone. So, what is this concept of habitable zone? It is quite simple. Biologists have observed that life forms we know of on our planet need liquid water to appear and survive. It doesn't mean life is impossible without it, but Earth-like life based on the chemistry of carbon, oxygen, and hydrogen probably needs liquid water. The liquid state for water requires quite specific conditions of temperature and pressure. Outside of these, water is either solid or gas. And Earth-like life, especially surface life, would be impossible. When a planet is too close to its star, the heat is too much, and stellar winds are likely to prevent a thick enough atmosphere from existing. With high temperatures and a very thin atmosphere, which means low pressure, liquid water cannot exist at the surface. But if a planet is too far from the star, it doesn't receive enough energy from it, and water turns to eternal ice. Of course, even outside the habitable zone around a star, life could theoretically appear in underground oceans, for example, but surface life probably not. Now, it's not because a planet is in the habitable zone that it is likely to harbor life. There are many more conditions of composition, temperature, pressure, and maybe a series of coincidences that make life possible. In the solar system, Venus and Mars are also in the habitable zone, yet no sign of life has been detected there. Though Proxima Centauri B is in the habitable zone, its size is relatively similar. A bit bigger, but its habitability remains very uncertain because of stellar radiation and brutal variations in energy its star sends. We don't know whether or not the planet is shielded from this, but there is a slim chance that liquid water exists if the planet constantly presents the same face to its star, like the moon does to Earth. When a body orbits another one, and at the same time revolves slowly on its axis, so that it always presents the same side, it is said to be tidally locked. The moon is tidally locked to Earth. If this is the case for Proxima Centauri B to its star, there must be a hotter side that receives radiation and a colder, dark side opposite the star. But in between, there could be a thin border region where the transition between extremes happens. Or if Proxima Centauri B has a magnetic field and is rocky, an atmosphere made possible by the magnetic field and maybe a regulation of its temperature by atmosphere, then the sunny face would have liquid water. There are many conditions necessary and a high probability that the planet is just a dead rock, or maybe not even a rock. But we cannot exclude the possibility of life only 4.2 light years away from Earth. But let's escape Proxima Centauri B and resume our journey. We are now going to accelerate even more than last time, because our next destination is OTS 44, 550 light-years away. OTS 44 is a planet so large that it could border on a star. It has more than 10 times the mass of Jupiter and is located in the constellation Chameleon. As we resume our journey, and because this planet is going to be very different, let's take a look at the various types of planets and stars that we know of in the universe, or that could theoretically exist. What is a planet, actually? The most commonly accepted definition is that a planet is an astronomical body orbiting a star, massive enough to be rounded by its own gravity, and which has cleared its neighboring region of other bodies by absorbing them or turning them into satellites. However, it's not massive enough for thermonuclear fusion to occur. According to this definition, planets are defined mainly by their size, with both a lower and an upper limit to what constitutes a planet. This definition disqualifies a few bodies that are big enough to be rounded by their gravity, like Pluto, for example, but not big enough to have absorbed planetesimals, protoplanets, around them. This definition of what a planet is remains a bit controversial, because it excludes objects of planetary mass based on what or where they orbit. There are satellites in the solar system that are bigger than planets, but they are not considered planets because they orbit another planet before orbiting the Sun. If the criteria of cleaning space was lifted, then Pluto would be classified as a planet again. But so would various bodies from the asteroid belt, like Ceres or Pallas. These are just conventions anyway. But whatever its definition, the term planet also hides a variety of bodies that can be completely different in their size and composition. What planets are made of? In the solar system, there are rocky planets. They have a hard surface and are mainly made of metal and rock. They also have an atmosphere made of gas. But the separation between the atmosphere and the surface is very clear. There are also planets called gas planets like Jupiter or Saturn. They're bigger and don't have a well-defined surface because they are a giant ball of gas, mainly hydrogen and helium. They can also be very dense. Actually, their cores are denser than rocky planets in the solar system because of their size, which compresses the core. Bedrocks are marginal on these planets, and they lack a hard, solid surface. Their density just increases progressively as you travel from the periphery to the core. There are other giant planets like Uranus and Neptune called ice giants. The structure looks the same as gas giants, but their composition is different. Instead of hydrogen and helium, they are made of heavier substances like methane, ammonia, water. We talked about this in previous stories already. But in astronomy, ice is not always water ice. It can also be other compounds like water, carbon dioxide, hydrocarbons. Ices in an ice giant do not form a solid icy ball like an ice planet. They float. So there is no solid surface either. But nothing says all kinds of planets are represented in the solar system. There are other types of planets, or theoretical types of planets, that have not been discovered yet, but could exist. For example, gas dwarf planets, or mini Neptunes. These are planets with a rocky core and a thick envelope of gas or volatile ices, like a crossover between Earth and Jupiter. Planets are called dwarfs when their total size, their radius, is up to 3.9 times that of Earth. Above this limit, they become giants. It is theoretical, but another kind of large gas planet could be made mainly of helium instead of hydrogen plus helium. If a small star loses enough mass, is downgraded to a planet, these would be expected to resemble a gas giant, but they would differ from them by their composition and formation history. Another theoretical type of planet could be ice planets. There are bodies in the solar system with a solid icy surface, like the moons Enceladus orbiting Saturn, Europa orbiting Jupiter, or Triton near Neptune. An ice planet would be a bigger version of these, big enough and independent enough to fall into the definition of a planet. None have been found yet, but there could be iron planets too. Rocky planets generally have a metallic core. When they form, heavier elements like iron tend to migrate towards the core, and lighter elements like silicate rocks stay closer to the surface. But a planet that would form mainly from iron, or that would lose its rocky mantle due to giant impacts, could become an iron planet. The closest planet to this model in the solar system is Mercury, the first planet from the Sun. In proportion, it contains a lot of iron. All these existing or theoretical planets are not random inventions. Their proven possible existence is a result of the planet formation process when a new planetary system appears. You know that according to the current state of theories about planetary system formation, or single star systems at least, it all begins with a large disk of matter, gas and dust, that progressively accretes due to gravitation. Most of the matter ends up creating the star, something to the magnitude of 99% of the matter available. Planets form with what is left of it on different orbits around the star. The remaining matter forms rocks that collide for millions of years, absorbing each other and giving birth to protoplanets that clean up their orbit or become satellites, smaller bodies. If we take the example of iron planets, they are expected to form near a star because presumably this is where protoplanetary disks consist of a lot of iron-rich material. Why iron and not another metal? It is because iron is a rather abundant element in the universe, the sixth most abundant. By mass, one element you are most likely to find in the universe, and by far, is hydrogen, the simplest kind of atom. It is followed by helium. When hydrogen nuclei merge in stars during thermonuclear fusion, it produces helium. So it is another abundant element that stars keep producing all the time. In third place, there is oxygen, followed by carbon and neon. We rarely hear about neon because it is quite rare on Earth. There are traces of it in the atmosphere, where it is a gas, and there is even less in the Earth's crust. There is little neon on rocky planets because it is highly volatile and does not form compounds that could freeze it to solids like oxygen does. So it tends to escape from planets in the early stages of their formation. It doesn't stay trapped in the condensing clouds of gas and dust that form solid planets like Earth. But it is a more significant component of the larger gas planets and stars. In sixth position comes iron, far above any other metal. This is a typology of planets by composition. But there are other ways of categorizing planets, for example by mass. The term super-Earth has become to name a type of exoplanet that is more massive than Earth, but still less than the giants of the solar system. Theoretically, a rocky super-Earth could be habitable, but gravity could be much higher than we are used to. Another concept based on mass is super-Jupiter, a planet that is more massive than Jupiter. Various of them have been discovered, including OTS 44, which we are on our way to visit. Yet another way to categorize planet is by their orbit. This is where the concept of hot Jupiter or hot Neptune appears. These would be gas giants or ice giants orbiting much closer to their star than they do in the solar system. And they are called hot because the proximity to their sun would mean high temperatures in their more superficial layers. As I mentioned before, the main difference between a planet and a star is based on mass. Stars are big enough to ignite thermonuclear fusion and become bigger energy producers in the form of heat, light, and other radiation. It also means there are bodies that are just under or above this limit, very big planets or very small stars. OTS 44, which we are now reaching, is one such body. It was discovered in 1998. It is not a planet attached to a star, but rather a free-floating object that has 11 times the mass of Jupiter, but only 1.1% of the mass of the Sun. We don't know exactly what it looks like, but it is believed to have a disk of particles of rock and dust about 10 times the mass of Earth. This disk could be in the process of accretion, creating a mini planetary system with a very small star at the center and one or several planets orbiting around it. It seems OTS 44 is just at the limit of planet and star, and this kind of object is called a brown dwarf. A brown dwarf is not massive enough to fuse ordinary hydrogen in its core, but it can fuse deuterium. Deuterium is an isotope of hydrogen. What is it about? Elements are defined by the structure of atoms. Common hydrogen, for example, has two particles, one proton in its nucleus and one electron. Any atom with these two particles is hydrogen. The nuclei of atoms may also contain neutrons, another type of particle, and the number of neutrons can vary. These different versions of the same atom are called isotopes. When a hydrogen atom also has one neutron in its nucleus, it is still hydrogen, but its properties are slightly different, beginning with the mass, which is a bit higher. And this particular isotope is called deuterium. Maybe you've heard of something called heavy water. This has to do with deuterium. A molecule of water is made of 2 atoms of hydrogen and 1 of oxygen. Most of the time, hydrogen has no neutron. Regular water on Earth is made of that type of hydrogen. But if the hydrogen atoms that combine with oxygen are the deuterium isotope, with an additional neutron each, the water it creates has different properties. It is a bit more massive, hence the name heavy water. It freezes at a higher temperature, close to 4 degrees Celsius instead of 0. One of the applications of heavy water is in the nuclear industry. In many nuclear reactors, water is used as the moderator. That is to say, the substance that slows down neutrons to facilitate their capture by a fissile material, so that nuclear fuel will become unstable and fission. An advantage of heavy water over regular or light water is that heavy water has a lower propensity to capture neutrons. It's logical because deuterium already has a neutron, so it facilitates reactivity inside the reactor. The nuclear fuel may be less enriched in fissile material. Returning to brown dwarfs. These are bodies that are massive enough to fuse deuterium, because this requires less extreme conditions than ordinary hydrogen. Deuterium fusion gives helium-3, a deuterium nucleus combined with a second proton, so it is no longer hydrogen. It is now helium, with an isotope of helium with the neutron from deuterium. That's why it's called helium-3, because of the particles in its nucleus, 2 protons and 1 neutron. Brown dwarfs emit a bit of light, nothing compared with larger stars, and this is why they are called brown. They are hard to detect by visual observation because of their low brightness, but in fact, to the human eye, they would probably appear magenta or orange-red rather than brown. Even more than with planets, there is a diversity of stars based on their mass or the stage they are at in their life cycle, which determines their kind of luminosity, size, and radiation. Currently, stars are generally classified under a system called Morgan-Keenan, with a letter and a digit indicating their temperature and luminosity. As stars appear and burn for millions or billions of years through the main stages of their lives and then die, their classification evolves. So let's take a look at some types of stars or stages in their existence. As we already started with brown dwarfs, there are at the lower limit of what a star is. You remember when we visited Alpha Centauri, we talked about the red dwarf around which Alpha Centauri B orbits. Red dwarfs are bigger than brown dwarfs, and they are true stars because they fuse ordinary hydrogen. However, their limited mass makes the fusion reaction relatively slow. so they are small-sized stars. Their surface is colder than others, and it is also believed that they can live much longer than bigger stars. Above this category in mass are stars like the Sun, which are sometimes called yellow dwarfs, but their precise classification is G-type main sequence stars. Their typology is based on their luminosity and radiation, but we can just retain the idea that they are rather similar to the Sun. These stars typically exist for around 10 billion years, way less than red dwarfs, because they burn their reserves faster. At the end of their life, when their hydrogen reserves in the core become exhausted, they grow dramatically in size and become so-called red giants. It happens because after billions of years of existence, their core has become rich in helium, the main product of hydrogen fusion. So they begin to consume hydrogen from their more superficial layers, which expands them dramatically. At the same time, the helium core tends to contract, which liberates gravitational energy. As a result of these two factors, the star may expand up to 1,000 times its previous size. When this happens to the Sun in several billion years, it should expand enough to absorb Mercury, then Venus, then Earth, and even Mars. At the same time, the surface temperature decreases, and this is why they are called red giants. Their luminosity tends to decrease. After this phase, it is believed that a red giant collapses on itself, abandoning a lot of its matter that keeps floating in space. These clouds of gas and dust are nebulas that may later participate in the formation of a new system. In the last stages of its life, now that hydrogen to fuse has become scarce in its core, a star of that kind begins to fuse heavier elements, beginning with helium. This is how new elements can be created from the most common ones, like carbon or iron, to the biggest, most massive atoms. But the remains of the star keep agonizing for a very long time, several billion years more, as a smaller body the size of a planet called a white dwarf. Bigger stars than the Sun also exist. They tend to have a shorter lifespan because they burn their fuel faster. When they approach the end of their life and begin burning helium, these massive stars become very bright and are called blue giants. Blue giants are fairly rare because they don't exist for a long time. Still, it can be millions of years, but this is not that much on an astronomical scale. Later, they go through the same expansion process as Sun-like stars and become red supergiants. You have probably heard of supernovas. A supernova is a phenomenon that may happen when a large star reaches the end of its life, either because it has turned into a white dwarf that explodes, or because a star that still has nuclear reactions implodes, suddenly collapses on itself. When this happens, the collapse of its core dislocates its external layers. At the scale of a galaxy, supernovas are relatively rare, but there are so many galaxies in the universe that it is estimated a supernova takes place somewhere every 2 or 3 seconds in the universe. But in the Milky Way alone, there would be 1 to 3 supernovas per century only. The supernova is such a powerful phenomenon. It releases so much energy in a few milliseconds that the dying star can suddenly become more bright than an entire galaxy. And they are important events in the universe too, because they disseminate the elements synthesized by the star during its life. And they create shockwaves in space. It is believed that these shockwaves are responsible for the formation of new systems. They will transmit motion to a nebula and facilitate the concentration of clouds of floating matter. This matter can then start to spin and accelerate due to gravitation and form a new planetary disk with a star at the center. White dwarfs, these dead bodies of stars, are very dense, and if the star was big enough, they may shrink even more and turn into neutron stars. Neutron stars are dark, small, but extremely dense balls of matter in which the forces at play are so strong that atoms shrink, and electrons and protons combine to form neutrons. The neutron star is made of atomic nuclei. The next stage, if the star was even bigger, may be the transformation into a black hole. Earlier I mentioned pulsars that emit very stable signals. It is believed that these stars are heavy white dwarfs, or neutron stars, the remnants of a large dead star that rotates fast on itself. So let's return to exoplanets now that we have seen OTS 44. Because we have one last stop to make before returning to Earth. We're going to visit one of the most Earth-like exoplanets identified, Kepler 438b. It was discovered using the transit method and confirmed in 2015. You remember the transit method is the measurement of how the crossing of a planet in front of its star dims the light. Its star is called Kepler 438, and it is a red dwarf located 640 light-years away from Earth. Kepler 438b checks a lot of boxes in comparison with Earth. It is in the habitable zone of its system, this region at the periphery of the star that is not too hot nor too cold. It is likely to be rocky and has almost the same size as Earth. Its radius is only 12% bigger. Its equilibrium temperature, that is to say, the theoretical temperature it could have given the stellar radiation it receives, would be around 3 degrees Celsius, 37 degrees Fahrenheit. The main concern we saw earlier with Alpha Centauri B is that it may receive large amounts of radiation from its parent star, which produces regular bursts of radiation. We saw earlier that liquid water was seen as a likely necessary condition for the appearance of Earth-like life, but to search for an environment that could harbor life is just one aspect of a larger field of study called Astrobiology, the study of life in the universe. How it may appear, travel through space eventually. What forms, what organisms can be called life? What life forms from other worlds may look like? This is a vast field of study, but one that is a bit paradoxical too, because it studies something we have no trace of at this point. Given that there is no organism to actually investigate, astrobiology focuses on the origins and evolution of life, the kinds of biospheres that could support it, whether extraterrestrial life exists, and how it could be detected. So it touches on many different fields: biology, biochemistry, astronomy, geology, and physics. And it concerns itself mainly with hypotheses that would be coherent with existing scientific theories. We talked about earlier that the search for life focused on carbon-based chemistry. This may sound a bit random or restrictive, as if we lacked imagination, but maybe not so much when we start defining what a living organism may be. It needs to interact with its environment, to find energy somewhere, to build itself. Carbon is a very particular element compared with others because its capacity to be part of many different molecules is unmatched by any other element. It is rather abundant too. The fourth most abundant element in the universe after hydrogen, helium, and oxygen. The energy required for it to make bonds with other elements to form molecules is just at the right level. The molecules formed are stable, but at the same time, they can react when put into contact with other elements. And that's a unique property, and probably the reason why all forms of life we know of on Earth use carbon. To understand how carbon chemistry is crucial, think about the cycle of eating, digesting, and breathing that keeps human beings alive. A large part of what we eat is carbon. It is a key component of not only carbohydrates, but also lipids, proteins, fibers, vitamins. When we digest these nutrients, we take bricks from them to maintain or build our organisms, and we also get energy from the breaking of carbon-based molecules. A part of the carbon is ejected through breathing. We take in oxygen and we take out oxygen and carbon dioxide. All of these transfers of matter and energy are only possible because of the particular properties of carbon. The thing is, no other element seems to be able to replace it. As far as we know, matter in the universe is not different on Earth. 1 light year away or 1,000 light years away from our home, the constraints are the same. And assuming life requires complex chains of molecules that can be broken and rearranged to transfer matter and energy, we see no other element than carbon that could be at the center of it. This is why the search for extraterrestrial life focuses so much on the chemistry of carbon and the conditions needed for it to become the basic building block of life forms. It is not a random option, and it actually looks like a well-informed guess to narrow the search for extraterrestrial life. Carbon and liquid water, which is another ingredient required for carbon-based chemistry to fulfill its potential. Another way to narrow the search when it comes to exoplanets is the type of stars. Sun-like stars are preferred because larger stars tend to have a shorter lifespan, giving life less time to appear before they die. Smaller stars, like the small red dwarfs, may not send out enough energy. But on the other hand, red dwarfs may not be such a bad environment because they exist for hundreds of billions of years, which gives a lot of time to life. A thick atmosphere that would heat the planet through the greenhouse effect could allow the temperature to be sufficient, even with not such a powerful star. There is a hypothesis called Panspermia, according to which life could exist throughout the universe, and that it could travel and be distributed by asteroids or space dust. It is possible that the chemistry leading to life with complex molecules may have appeared quite quickly in the history of the universe, maybe after a few million years only. We think the universe is 13.8 billion years old. The basic blocks of life may have formed spontaneously in nebulas or in the first planetary systems. They were made of elements that are relatively abundant, so these building blocks of life may have been distributed to planets as they formed, waiting for favorable environments to combine further. It is impossible to make rules because Earth is the only example we have, and it is true that life on Earth appeared relatively quickly in its earliest forms when Earth cooled down and had liquid water. Earth has supported life for billions of years already. Another aspect of panspermia is the possibility that microorganisms can survive the effects of space, the void, the intense cold or heat, the radiation. These are extremophiles, organisms on Earth that are able to survive in conditions that would kill most others, like hundreds of degrees or staying frozen for years. Maybe these organisms could be ejected with other debris when a planet collides with an asteroid and stay dormant for years or even centuries until they randomly land on another planet, where they will become active again and colonize a new environment. These are just hypotheses that sort of fit with scientific theories. They are not absurd, but there is no hard evidence that this ever took place. Is there life on Kepler 438b? We don't know. It is so far away at 640 light years. It is hard to imagine human beings ever going to check. It sounds absolutely improbable. But the idea of flying to Mars would have sounded equally absurd 3 centuries ago. We are now maybe just a few years from achieving that. So perhaps our children will find a way that we cannot even start to think of now to travel faster than light and reach these faraway worlds. For now, our journey is nearing its end. We are now going to return to Earth even faster than we left. You can now stop focusing and start to dream of all the stars, comets, and clouds that we are crossing on our way back to Earth. I hope you enjoyed our adventure, and I invite you to discover and learn more. Now you can let go and sleep, or if you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.